Before watching this video, you already should have gone through the videos covering the rules on drawing Lewis structures, resonance, and formal charge. Now we're going to look at the exceptions to the octet rule, and there's three exceptions that we're going to look at. The first is free radicals, the second applies to elements that have incomplete octets, and the third applies to elements that will have an expanded octet. So if we start with free radicals, a free radical by definition is a species that has an odd number of electrons. And an example of this is the structure that you see in front of you that is NO, or nitrogen monoxide. If we look at this structure and we start using what we know about the rules for drawing Lewis structures to try to draw this structure, the very first thing we're going to do is start with determining the total number of electrons that we have for this structure. So in doing so, we know that our nitrogen is going to contribute 5 valence electrons to the structure. Our oxygen is going to contribute 6 valence electrons to the structure, and that gives us a total of 11 electrons for the structure. Up to this point, when we've seen an odd number of electrons, it's been in the context of an ion. And in those cases, we often have the ability to make a correction to the electron count, get back to an even number of electrons by correcting for that charge by adding or subtracting electrons. But in this case, we have a free radical. It is an uncharged species, so we have the same number of protons and electrons in this structure. So that means that we've got 11 electrons and there's no correction that we can apply. So as we start drawing this structure, what we're going to do is we only have 2 atoms, so we'll place our atoms next to each other, like what you see here. And then we're going to start completing the octets for our outer atoms. So in the structure right here on the left, I'm going to start by completing the octet on the nitrogen, so I'm going to give the nitrogen 6 electrons. If I'm following my electron count, that means that I will have 3 electrons left, and I'll put them on the oxygen. So in this structure, we have a total of 11 electrons accounted for, and we have followed all of the rules that we know for drawing Lewis structures. So now that as I look at my atoms, my nitrogen has an octet, my oxygen does not have an octet. So what I need to do is similar to what I did for drawing Lewis structures with central atoms. I need to look to my outer atoms for additional lone pairs that I can share. So that means that in the case of this structure, I'm going to be looking to my nitrogen for additional lone pairs to share, and I'm going to take this lone pair, give it to the oxygen, and that's going to give me this structure here, where my nitrogen still has 2 lone pairs, my oxygen has the lone pair and the lone electron, and I now have a double bond between my nitrogen and my oxygen. As I look at this structure, my nitrogen still has an octet, my oxygen sees 2 electrons in the lone pair, 1 electron here in the free radical, so that's 3, and then 4, 5 in this bond, 6, 7 in this bond, so a total of 7 electrons. Okay, my oxygen sees a total of 7 electrons. Now we know about getting to an octet, and we know about sharing additional electrons in an effort to get the atom to the octet. So let's see what happens if I take another lone pair from my nitrogen and share it with the oxygen. And if I were to do that, that's going to give me this structure here. So if I were to share one more lone pair, I would get to this structure here. And if I look at this structure, I see that my nitrogen has an octet. It sees 2 electrons in the lone pair, 6 in the triple bond for its octet. My oxygen, however, sees 6 electrons in the triple bond, 2 electrons in the lone pair, and then this lone electron for a total of 9 electrons. Because it is forming these bonds with its orbitals from the second shell, the 2s and the 2p orbitals, those are the orbitals in its valence shell, those orbitals only hold up to 8 electrons. So the oxygen simply cannot hold 9 electrons, and this is going to violate its octet. The oxygen simply doesn't have the orbitals to accommodate that number of electrons, so this is not a valid Lewis structure. So in this series of structures, this is as good as we can do. We can get the oxygen to 7 electrons, but we can't go beyond the 7. However, when I started drawing this structure, after I connected my atoms, I started by completing the lone pairs on the nitrogen. If over here I started by completing the lone pairs on the oxygen instead, that's going to give me this initial structure where all 11 electrons have been distributed. First to the oxygen, then the remaining 3 electrons were placed on the nitrogen. So now as I look at this structure, my oxygen sees its octet, my nitrogen does not see the octet, so that means that my nitrogen needs more electron density. Nitrogen currently sees 2, 5 electrons. So I'm going to take a lone pair from the oxygen and I'm going to share it with the nitrogen. And if I take that lone pair from the nitrogen and share it, that gives me this structure here. In this structure, my oxygen sees its octet. In this structure, my nitrogen sees 4 electrons in the double bond, 6 including this lone pair, and then 7 including the lone electron. So it is not yet to an octet, and just like we saw over here, there's nothing more we can do to get that nitrogen any closer to the octet because we only have the ability to share 2 electrons from the oxygen, and that would take the nitrogen beyond its octet. So this structure here is as good as we can do. In order to understand which of these 2 possible structures that have followed all of the rules for Lewis structures is going to be the best Lewis structure, we are going to use formal charge. One of the things that you need to know as you do this is that the lone electron will count towards your non-bonding electrons in your equation because it's an electron that belongs just to the atom on which it resides. Pause the video and calculate your formal charges and choose the best structure for nitrogen monoxide. So as you calculate all of your formal charges, in the structure on the left, where the free radical resides on the oxygen, our nitrogen carries a formal charge of -1, our oxygen carries a formal charge of +1. The calculation for the nitrogen follows all of the rules that we've laid out so far. The calculation for the oxygen includes the fact that it comes to this structure with 6 valence electrons. In the structure, it has 3 non-bonding electrons in the form of the lone pair and the free radical, and in this structure it sees 4 electrons in bonds, so 6 minus 3 minus half of 4 gives me my formal charge of +1. So I have the sum of my formal charges that add up to the overall charge of this molecule, which is 0. I have small formal charges, but let's compare that to what we get in the second structure. In the second structure, if I calculate the formal charge on my nitrogen, I'm going to take into account the fact that it comes to this structure with 5 valence electrons. In the structure as drawn, it has 3 electrons that are non-bonding electrons, 2 from the lone pair, 1 from the free radical, minus half the number of electrons in bonds, which is 4 from that double bond. So 5 minus 3 minus half of 4 gives me a formal charge of 0. For the oxygen, I know that anytime I have an oxygen with 2 bonds and 2 lone pair, it's going to carry a formal charge of 0. So that as I compare these 2 structures, I know that it comes down to my formal charge. The structure that has the better set of formal charges will be my best Lewis structure for the nitrogen monoxide molecule, and that's going to be the structure here on the right. That's going to be my best Lewis structure for the nitrogen monoxide molecule. The second exception to the octet rule applies to elements that will carry an incomplete octet. This rule is going to apply to the elements of group 3A on the periodic table, and we will mostly see this rule apply to elements like boron and aluminum. Anytime you see those elements, you need to remember this rule. The incomplete octet rule tells us that the elements of group 3A, like boron, will be stable with only 6 electrons, so not getting to that full octet. And if we look at a few examples, we can understand why that is. In the first structure here, I've drawn the structure of BH3 for you. As you go about drawing this structure, you know that the boron is going to contribute 3 electrons to the structure. We have 3 hydrogens that will each contribute 1 valence electron to the structure, so that we have a total of 6 electrons in the structure. As I place the boron as my central atom, knowing that hydrogen is never a central atom, and I bond the hydrogens to it, this is the structure that I come up with. This is really the only structure you can draw when following the rules for this molecule. We're out of electrons at this point, and my outer atoms do not have any lone pairs, so there's no way that I can make double or triple bonds in an effort to complete boron's octet. This structure has 6 electrons, and this is how all of those electrons are placed into the structure. When I look at my formal charges, a hydrogen with 1 bond will carry a formal charge of 0. If I calculate the formal charge on the boron, I'm going to use the fact that it comes to the structure with 3 valence electrons. In the structure, it sees 0 electrons in lone pair, and in this structure, it sees 6 electrons in bonds. So 3 minus 0 minus half of 6 gives me a formal charge of 0. So that in this structure, one of the reasons that BH3 is a stable molecule is because all of our formal charges are 0. If we look at another example like BF3 here in the middle. If I draw this Lewis structure, my boron contributes 3 valence electrons. I have 3 fluorines that each contribute 7 valence electrons. That's going to give me a total of 24 electrons for the structure. As I choose boron as my central atom, place the fluorines bonded to it, and complete all of their octets, I use all 24 of my electrons. Now in this structure, I do have outer atoms with lone pairs that I could potentially use to make double bonds with the central atom in an effort to complete its octet. But watch what happens if we do that. If I use this fluorine to make a double bond, I get a structure that looks like this. And in order to understand if this structure is better or worse than the original structure that we started with, we can use formal charges. Pause the video and calculate the formal charges on this structure and this structure. So as you calculate the formal charges, in the top structure you find that we have all formal charges at 0. In the bottom structure we see that our 2 fluorines that have 3 lone pairs and 1 bond carry a formal charge of 0. When we calculate the formal charge on the fluorine that has shared the additional electrons with the boron, we get 7 minus 4 minus half of 4 gives me a formal charge of plus 1. When we calculate the formal charge on the boron that now has a complete octet, we find that its formal charge is minus 1. So one of the tools that we had to help us identify a best resonance structure is understanding that formal charges of 0 are a very good thing for our molecule. So that this structure here, where all of our formal charges are 0, this is going to be the best Lewis structure for our molecule because all of those formal charges are 0. When we look at this structure down here, having a fluorine with a formal charge of plus 1 is a huge mistake. Fluorine is the most electronegative element on the entire periodic table, so that this is a formal charge that it's not going to be happy with. So this is very bad in the context of a structure. Boron is less electronegative than fluorine, and boron has a formal charge of minus 1 in this structure. So that overall, we can conclude that this structure down here is not the best Lewis structure. It is the structure, the first structure we drew, and whenever we see boron with just 3 bonds, it will carry a formal charge of 0. Even though it doesn't have a complete octet, it will still be happy and reasonably stable because of that formal charge of 0. Now I do want to make sure that you understand that our elements in group 3A can have an octet, but anytime they do have an octet, they're going to have a formal charge as a result. If we look at the structure of this borohydride ion, the boron comes to this structure with 3 valence electrons. I have 4 hydrogens that each bring 1 valence electron, giving me a total of 7. Because this is an anion, I have to add in 1 additional electron to correct for that charge, and I have a total of 8 electrons in the structure. As I place all of those 8 electrons in the structure, I get a structure that looks like this, where the boron is my central atom, and all of my hydrogens are bonded to it. This is an ion, so the structure also belongs in brackets with the charge outside. Now, when we calculate formal charges, we'll find that all of our hydrogens have a formal charge of 0. When you calculate the formal charge on the boron, you will find that boron's formal charge is equal to minus 1. So anytime you find boron or aluminum with a complete octet, it will carry a formal charge of minus 1. It can happen, but that is going to be a molecule that's going to be reactive in the sense of trying to get rid of the electron density that it carries, whereas a molecule like this one or this one is going to be reactive in the sense that they're going to be very good electron acceptors. For those of you that go on to organic chemistry, we'll see these molecules act as very good electron pair acceptors in some of the chemistry we look at in that course. And we'll see this molecule here act as a good donor of hydrogen with the electrons in an effort to reduce the formal charge that we have at the boron.